Thank you, Ruben. Thank you for this very kind introduction. Thank you for coming today. I was not expecting such a large crowd. And I hope that you enjoyed the talk today. You will see it's not it's more a concept. It's more about the concept of this platform, which is a project that started last year. So we don't have a chemical result yet, but I think it's more for presenting you this project. I'm very interested to know what are your opinions about it, or if you have questions or any other comments about it. And so we are based at the EPFL, as Ruben just explained, and we are called the SwissCat Plus. So I'm going to. Okay, so sorry. So the SwissCat Plus project is basically is a project that was funded by the EPFL Confederation. So the government decided to decide every year that they fund a project, 3 to 4 projects for 4 years. This project can be renewed after 4 years, and so basically potentially 8-year funding. The first round started in 2021 and will last until 2024. And next year we will apply for the second round of funding. The first round of funding is 25 million, and the second one is 15 because, of course, the infrastructure is already here, and therefore you have less investment to do. This money is split in two. It's between the ETH Zurich and the EPFL. It's 50-50. The ETH Zurich will focus on the heterogeneous catalysis, and the EPFL the homogeneous catalysis. And this is the reason is because this project was written by 2 professors, Professor Kramer at EPFL and Professor Copré at ETH Zurich. And what they had in mind was this the idea to develop. Perfect. Thank you very much. To develop a new platform that is autonomous for the optimization and the discovery of catalysis. And they had many ideas that they put in this proposal, just broad ideas, but practically there was a difference between put it on the paper and how to do it in a laboratory. And these ideas were, it has to be data driven, it has to be automatized, autonomous. We want to do continuous development, meaning that we want to collaborate with companies and with other technologies to develop the field of automation in chemistry. It has to be a landmark in the field of automation. We want it to be recognized for its work. It has to be open access, and of course it has to be focused on catalysis. And for this, they brought a team. The first person that Nikolai recruited was Pascal Miéville, Dr. Pascal Miéville, who is now the executive director of this platform. And before, he's a very good analytical scientist. He used to be in charge of all the NMR platform at the EPFL. And in general, he's a brilliant person that knows a bit everything on everything. Then he recruited me to take care of the synthetic part of the platform. Then we have also the Uriel that is here also today with me, and we are working with Cisco to have a look at your platform and see what you are doing here, because I think it's very interesting to get inspiration from people who have already set up such platforms. And we recruit 2 more person that have an atypical profile for a chemistry lab, meaning, sorry, a robotic engineer and an IT specialist. And these are crucial to develop such a platform, because as you will see, when you want to do something in automated chemistry, you need to develop new tools. You need to integrate tools together. And this, we are not able to do it. And these two people, they are very talented, and they are extremely important for this project. And we had, of course, Heidi that helped us with all the administrative tasks. So it's a small team that is growing. We will be recruiting more people in the future, little by little. We'll have a PhD that will come, bachelor students and master students also. The roadmap of this project is a bit simple, challenging but simple. Basically, we really started in 2021. We designed the lab, we constructed the lab, we thought about what do we need in terms of machine, what do we need to acquire, what are the best machines for our project. And at the end of 2021, we've done this and we know what we will go with. The lab is being finished. In 2022, that will be used for installing the machine, and 2023 to calibrate and to validate all the laboratory. We want to take time for this because it will be the base for the future. So it means at the end of 2023, we will have a lab that is able to do HT, that is able to analyze reaction. At the end of 2024, we want to start, working on specific projects, acquire data, and try to see if we can use this data to feed back into those machines so that we start to do iterative loop of optimization. Then we use the next year to acquire more knowledge about this platform. Of course, there will be other developments, but the ultimate goal at the end is that in terms of catalysis is how do we inject novelty? How does this platform that is able to learn from itself can then come and suggest you a new catalyst? How can it suggest a structure that would suit what reaction you want to do? And I think this is a very high challenge. It requires lots of development in theory as well as in the experiment. But this is a bit the goal that we fix ourselves at the end of these 8 years. And to drive us through this endeavor, we listed a few key ideas, something that we think are very important to keep in mind. The first thing is, even if these platforms are doing chemistry, the main goal is to have a high quality data generator. The value in this platform is not the reaction itself, is really what data we can get from this. And the fact that it will be clean data with high quality. This is where we can start with machine, we can control what we are doing, and we can use that for prediction and other suggestions. We want a complete integration of the sample of the data, meaning that we don't want human to start having a role at some place, because we want the workflow to be as automatized as possible for the reason I just explained, because when you are using robots, you can acquire the data and you can control it. We want to use, especially in the domain of analytics, a lot of it is done so that the human can understand what you are doing. If you take, for example, the NMR, all the Fourier transform of the FID is made so that the human can interpret the NMR. But the machine can very well work on an FID. It has all the information it needs, and it has even more information, in fact. And so this is something we want to develop in the platform, is how to get as much information as possible. The GIGO acronym, maybe you heard it, is garbage in, garbage out. If you feed with bad quality data your system, they will give you bad quality results. And this is something we want to bring in the chemistry, in the experimental chemistry field, is how do you bring quality control? How do you validate your experiment? You know what you are, how much temperature you're putting, how much, where are your sample coming from, etc. And want to be sure to bring this high quality in the system. So again, later on, you can use this data and compare it through the years and compare it with other experiments. Adopting a machine point of view. This is more for the design of the platform. Sometimes we want to automatize things as a human would do. The example that Pascal is taking is how you do the dishes. If you ask a human to do the dishes, he will take a sponge and scrape the plate and go to the next one. If you automatize that, it's not very efficient. If you want to automate that, use a dishwasher. You load everything, you close the door, you start the thing, and you do something else. And I think this is a bit what we try to implement in this platform. The last thing is machine learning is coming everywhere. It's very useful, but we will use it. We are very open to it, but we will keep very critical, and we need to be sure we know what we are doing and we are looking the right things. In terms of operations, so what have we done so far? So this, as I explained, the EPFL gave us the aisle of a building, and everything was demolished, and we restarted from scratch. And what you can see here is the lab. It's 27 meters long, 7 meters wide. And this was actually last week that they they delivered this. There is nothing on the floor. The goal is to have a clean surface so that we can modulate it if we need to move things. And all the energies are coming from the ceiling. As you can see, this crazy network of gases, because each of those round things is basically an input where you have all the gases and energy, electricity, and things like that. So it's highly dense, it's highly complicated in terms of engineering, but in the end, it will be a very useful lab for what we are trying to do. Our colleague or robotics specialist is really good at doing some 3D representation, and this is what we have in mind for the lab. The lower part will be dedicated to the synthetic part, and the upper part will be for the analytical. We have developed collaboration with different companies, because instead of just purchasing their machine and getting what they have, we explained them that we want to do things a little bit differently, and you need to do some development for this. And so we wanted to have an agreement that they invest in their products, so to develop together some of the tools for the future. And we have ChemSpeed for the synthesis, Agilent for the analysis, and Bruker for the NMR platform. The NMR that is just here. I don't know if you can see it. For the automated synthesis, which is what I'm most familiar with, basically we'll have two main glove box from two big platforms from ChemSpeed, which are called Swing XL under glove box, and then let's say a normal standard glove box system that will be filled with robotics that we are developing to develop new tools for whether solid handling or solid standardization or preparation of samples, and the storage unit. And then we will do a custom tunnel for transfer between all these different platforms that will, of course, include some robotic inside. And here, I don't know if you see, there is a robotic arm that will be able to pick up whatever sample is coming out of this system and send it to the analytical platform. And I will come back to this later. Basically, the two ChemSpeed system, I mean, it's very dense, and there's nothing to really see. This is the view from top with all the equipment that we decided to get. Basically, the goal on the HT was to have be able to process hundreds of samples per day of reactions. So we have classical solid sampling, liquid handling, the heat, cool, stir, shake, the pressure, photocatalysis, and all the other peripheral tools. And then we have a sample preparation also system that can do very similar system, but it's not made for reaction. The goal is really we can work in parallel. One is preparing the sample when the synthetic part is running the synthesis. We have some collaboration with the HEIG VD, which is an engineering school in Switzerland, for things like how do we standardize or process. It's very important. So we wanted to simplify as much as possible. And for example, one of the standards that exists is those SBS plates that you use for 96 well plates, for example. And we want to use all of workflows around this. And how do you go from standard compounds that you buy? They come in various bottles, various size, various shapes. And how do you automatize their transfer into standardized system, taking all the complexity of contamination and things like that you need to really pay attention. So these are the kind of development we are doing also in the field of automation in synthesis. For another thing, I didn't show it specifically, but there will be also a platform for optimization. This is not high throughput this time. This is really to study more kinetics of reaction on larger scale. So this platform is another ChemSpeed platform that will have three 250 milliliters reactors that you can also automatize, and you can also inject liquids at high pressure. And the goal in this case, the challenge is to bring inline analysis, and we will have inline NMR and inline IR system. The analysis part, again, this is less of my job, but it's very important because we'll have high throughput experimentation. Therefore, you need a very efficient system to process all these samples and highly automatized. And the strategy is to have two lines, one where you need characterization, one where you just need to get your observables, let's say maybe a yield or a conversion or an E. For the characterization, it's prep LC for the separation, and then it's split in two using Agilent technology, and one goes to NMR and UVVs, one goes to IR, and then chiral SFC for chiral separation with circular dichroism, and then mass analysis. For the fast system, it will be LC that is sent to an SFC in the similar way with mass analysis. And for the inline analysis, the NMR and the IR. For the robotics that are being developed, this is really interesting. And this is all about how do we transfer samples in the lab in the most efficient way. And you can see there have been some papers or some groups that have developed those platform that moves, and they have an arm, a robotic arm on it. And at the beginning, we thought about having one of those, but realized that in the end, what we need to move is a small plate. And this was overkill to move such a small thing. They weigh 200 kilos. They cost 200,000 Swiss francs. And in the end, if you take an arm, you can buy 10 robotic arms for the price of one of those platforms, and these cost a few hundred francs. And you can build a lot of them. And if you have a robotic engineer, they know how to make dozens of them and how to control them in a way that you never have to think about charging, or you never have to think about who's doing what. They will behave as, you know, those drones that you see in the sky where they behave like swans. Basically, this is the same, but in 2 dimensions. And so he builds this robot from scratch. This is guided by laser in the front. And this is really how the samples will move through the lab. And these robotic arms are what they're called collaborative, meaning that you can have it on the desk. If it moves and it does its things and it touches a human, it will stop. So it's very safe, and you don't need any particular precaution. And they are very easy to use because you basically take them in your hand and put them where you want them, and then it registers the position and the movement, and then it reproduces it. So they are, in fact, extremely easy to use and to integrate. And this is a bit the strategy. I don't know, I showed you earlier, I didn't point it out, but here you can see on the lab, there is this little platform above our heads. And this is basically where those small robots will move around, go to different stations, whether the synthetic station or analytic station will be picked up by an arm and placed in either whatever analysis you need to do. And like this, you sort of have a lab that is completely automated in terms of sample management. A part that is very, very important, but I will not spend too much time because I think would be an hour in itself, is the data management. I explained that in the end, this platform is very important to collect data. And you need to think about all these different parts that I talk about need to be controlled by something, and they need to also receive all the data, aggregate it, and so that you can use it later on. And in itself, it's a very complex layer system. There is, there are companies that will that will tell you, okay, we have integration software that you can buy, But in the end, as soon as you're looking for flexibility or customization, these things are not anymore usable. So we will use as much as possible what exists. There are tools like Scylla, Nime, Slims that are open source, that are developed for standardization of communication protocol, which are very important. If you need to plug a balance from Mettler Toledo to a 6-axis robotic arm to a ChemSpeed platform, you need also a lot of standardization in this field. And this is a big challenge. And this is also, I think, the success of this project can be done or not in this part. So I said I was not going to be too long. I think it's fine. As a conclusion, I think this sort of platform will become more and more frequent in labs. There are many of those in companies, in academia, and you can start to ask yourself this question: what do you do with all this data that you get? You know, you can start to switch from a deductive way of logic to an inductive way of logic, where you have all these results, and from all these results you try to find find the trends and find something that has a sense. You can already see some of these papers in the literature nowadays. You have lots of data again. How do you are sure that those machine learning algorithms that give you those very nice correlation are really linked to causation? How do you validate all this information? And how can you reduce as much as possible the human bias in your experimentation? How do you train the future chemist? I mean, as you see, I'm a synthetic chemist, pure organic methodology and total synthesis. And today I have to talk to IT engineer. I have to talk to robotic engineers. I feel like in this field of the chemistry, you have to look at many different skills and different horizons. And what will look like a chemistry lab in 2030, if you have robotic arms, drones, you could think if you have no more human in the lab, you could imagine having this lab somewhere in the basement where no one goes, but you control it from your desk somewhere else. You don't need to be present in the lab anymore. So yeah, this can be some thoughts about the lab of the future. So I hope this was a clear and interesting presentation. I thank you very much for your attention, for being here today. And if there is any comment and question, I'm very happy to answer those.
Thank you, Florian. It's very interesting talk. The floor is open for questions, curiosities that you may have about the platform, or anything that it was not clear from Florian's presentation. So it's a new platform that it's going to be potentially implemented soon.
Hello, thanks for the interesting talk. I have a question or curiosity. I've used the HT facilities we have here, and one of the things that can slow things down is when you're using things that don't dissolve particularly well in solvents, and you have to add things as slurries. I was just curious, how do you think you'll be able to overcome something like that when you're trying to set up hundreds of reactions a day and things like that?
Yeah, no, so that's liquid handling in robotics and chemistry is pretty much solved. It's a very good, it's a very mature technology. The solid handling is not at all. Powder can have many different properties, etc. So what people usually do is they prefer to add as a slurry. So you do some really high intensity mixing and hope this is stable enough that you have to dispense it. I agree that it's not convenient and it's hard to control precisely what you're doing. I think there are solutions nowadays. If you could dispense the powder directly, efficiently, instead of in a slurry, that would be the solution. And this is some of the tools we are trying to develop, is how to dispense quickly and precisely small quantities of powders. because this is not, you can have precisely but slow or fast, and yeah, you know, you don't really know what you have in the end. But I agree that this is the solid handling is really where there could be some development.
Thank you very much. I think it would be really interesting to see how you get over that problem. So
I hope in a few years I can come back and show you what we managed to do in this field.
Thanks, Florian, for the talk. It has been really, really amazing. So I went to ChemSpeed a couple of years ago. So I went to see the evolution, because one of the questions was about the solid, because when I went there, they told me, so basically my chemistry has to be very precise. So I guess that they have evolved, and now they try to encapsulate in glass like the son of the solid, so you can prelude like pre-dose what you need. But are you using that? So because the problem was that they told me that mix were like it was a problem. So like 1-2 milligrams, and when you are thinking about additives, sometimes you don't add more. So can you solve that problem?
We hope. No, I see. So the technology you're talking about is they create small ampoules, small glass
Like
capsules.
shake and breaks.
Yeah, exactly. It breaks under pressure. I think it's a very interesting technology. It has a few drawbacks. It's first, you still have to weight precisely the small amount. So this is, first of all, taking some time. The second thing is it's quite big. So you have quite a dead volume in these things. So you know, if you need a 20 ml vial to put half a mg, it can have its limitation. I know that it can be efficient, maybe more in the optimization part, where you could have maybe larger quantities. You are not in a high throughput experimentation, and you need to work with you can work with large volume reactors. So I believe this is more interesting, but at the moment we didn't choose this technology because I don't think it will make our workflow faster.
But can you wait 1 milligram with precision?
You can wait. So dispensing 1 milligram is feasible. They have different tools. They have a capillary tool, sort of capillary syringes now, where you can dispense a small amount precisely, but it will be slow. So it means if you take 3 minutes to dispense a compound, then if you do you know, hundreds a day, it's a bit complicated.
And the second question is, when I asked them to work under argon or nitrogen. So because what they do, as far as I remember, is to modify a glove box and to put the robotic arm, but that means that you occupy a lot, so you are losing a lot of space. So what are the conditions? Can you run the reaction under argon? So are you able to tune the son of the platform, the string one that is bigger and work as a glove box? Because what they told me is they cannot secure 100% that you are going to be as controlled as an M-Brown glove box. You know what I mean?
I mean, the product that they sell, I mean, they can have M-Brown glove box. So they have their custom M-Brown system.
But with the arm, like you occupy so much that you don't have so much space inside.
I mean, yeah, maybe then you lose. That's why we have small empty glove box, so that they will be dedicated for any robotic arms that we put in them, and they are dedicated for that.
So can you run reaction like are very sensitive to oxygen?
Yeah. I mean, everything will be under argon. That's why we have this tunnel that we plan to have, so that it can communicate between the glove boxes.
Beautiful.
More questions? I have mainly a curiosity, like this is a very nice initiative. I really like it. So in parallel of that, like EPFL and ATH are also working with academic like curriculum to prepare the human resources, because like, I mean, nowadays, I mean, it's just a starting point, but if in the future that will be successful, then many more labs like that will happen. And then I'm curious if it will be more beneficial to have such a multidisciplinary work, like, well, work human resources. So like a IT guy, a person doing like synthesis, or just to prepare a chemist that then knows a bit of everything, so that, you know, you have this figure of chemist that will be also able to work in robotics. I don't know if like also in
master like they are working with to prepare this new generation of chemists apart from new generation of tools for doing chemistry? Thank you so much.
Hi, thank you for a very interesting talk. I gotta say, I'm quite conservative with my chemistry. And I just have a question. So how are you going to compensate for basically the ineptitude of chemists? Because a lot of fantastic reactions are found because chemists mess up. Are you just going to find this out by just data, just hard, solid data?
Yeah, I mean, it's a very interesting question. It's a question we ask ourselves. So in a controlled world, how do you bring back serendipity? It's a complex answer, but how could we make some? I mean, there's nothing wrong of thinking, how do we make this machine more stupid, more random? It's a complex question. I agree, but yeah, I think I mean, in the end, the chemist who messes up still observes something and draw a result from that. He's not passive, he's not just doing something and then something happens. He's still observing something and he's still noticing something that shouldn't have happened. Or he's coming back to his data and say, wait, I put the wrong reagent and it's still working. So it's not completely passive. So maybe we can think about how machines can adopt this behavior.
Yeah, and my second question kind of follows on from that. Like the observation. So when I've just thought about low density polyethylene. So this was a white waxy solid that people just noticed. Can you teach a robot to notice this kind of side product?
I mean, if you know that, I mean, you have to know first that this kind of side product can happen. So you can have cameras. It's very, now vision is very well defined. So you can you can take a picture of the reaction. You even have cameras that go in the reaction. I mean, it depends. If you have the tools to measure it, then of course you can do it. If you don't, I mean, then you will miss it.
Okay, thank you.
Any other question?
Sorry, Ruben, we're running out of time and we have still some questions in the chat to answer.
One more though, okay? Just one more.
Okay, one more.
Hey, yeah, thank you for the great talk. I guess a lot of emphasis in the presentation was kind of placed upon, like, I'd say, batch.
I'm going to get closer because I can't hear you. Sorry.
I guess a bit of emphasis on the presentation was placed upon, I'd say, batch high throughput screening. I was wondering if flow techniques were ever considered.
If flow
techniques.
Flow techniques. So yeah, it was a choice. We decided to focus on batch. I think the flow it's a whole field of automation, of data. But in the end, if you're trying to do discovery in catalysis, batch makes more sense because you want to run many different reactions, many conditions in parallel. You want to compare them. I'm afraid in flow, I would see it more in optimization, where you have a more focused field goal. But I'm afraid for exploration, batch is more suited.
All right, yeah, that's great. Thank you.
Berta, are there any questions in the chat?
Yes, there are some. So Nuria Lopez would like you to comment on more on the data, the types of files stored, etc.
Comment more on the video, more on the data. Okay.
Yeah.
Can you repeat the question? Because I think
Yeah, can you comment more on the data, the types of files stored? Maybe if she's still around, I can invite her to talk herself.
The question is how you store the data, how you protect
Yeah,
the data?
on the data, types of files stored. Okay. I don't have any other. Okay. Is it characterization, testing, the types of data?
Oh, maybe we can have a look at it.
Okay.
That would be better.
Yeah, it's a Q&A section. Down right.
So where is Nuria's?
On the
Oh, can you comment more on the
data
data
type
types
of
of files being stored?
Okay.
Okay.
Okay, so for data, okay, we are not that far into what type of format. I mean, the IT. I had a quick discussion with the for IT specialists, but at the moment we don't know exactly how this will be done. There is a lot of question about how do we store and how do we record the data so that it makes sense for machine learning, for exploitation of this data, but also for communicating this data outside in an efficient way. I mean, in the end, all these machines, they will send us some output. How can we use that, let's say, in another platform? Someone can just use this file and have, be able to reproduce the experiment we have done. So there are many questions around what comes out of such an experiment, and I think it's almost a discussion we need to have between the people who have these platforms, because it can have a huge impact if you look in the long-term use of this data. So standardization is definitely an important aspect of it. I don't know. I hope it answers the question.
Berta, are you going to read the next one, or shall I do that?
If you want to do it, go ahead.
Okay, next question is from Gisela. Well, two questions, quick ones
Okay.
though. Is the PrEP LC an SFC chromatograph?
No, the PrEP LC is HPLC, and then there is another Carol SFC, but it's not PrEP.
Okay. And the second question is related to the glove boxes. The glove boxes where ChemSpeed robots are installed, are the classical ones from ChemSpeed or glove box, or are glove boxes from a glove box manufacturer?
So ChemSpeed glove box, basically they are custom from M. Brown. So they are ChemSpeed themselves don't do glove boxes. They just have them customized to fit their robotic platform.
Are there any other questions, Berta, or not?
No, that's all.
Okay. Well, I think we managed to get that.
So,
So
yeah,
okay. Well, thank you, Berta, by the way. So
you're welcome.
well, and yeah, before we just close the session, please join me by thanking Florian for this very unusual yet interesting talk. And yeah, thank you very much.
Thank you, everybody.